esters at the alpha position are less acidic than ketones at the same position. That's because the enolate is destabilized by electron donation by oxygen nearby. Now let's talk about amides. Amides have a pK of about 30 at that position, at the alpha position. And recall, the pK of esters at the alpha position is 25. Let's draw the structure for esters again. So something like that is a general structure for esters. And remember, this is the alpha position. If the ester is deprotonated with a suitable base, such as LDA, and of course LDA is a suitable base because it comes from an acid whose pKa higher than 25. The pKa here is 25 for esters. So any base that comes from an acid whose pKa higher than 25 is suitable enough, or is suitable to deprotonate esters at the alpha position. So we get this corresponding enolate. Of course, you get initially the carbanion, which you can stabilize by resonance to get the corresponding enolate. Not only this, there are 2 lone pairs obviously on that oxygen, so which can be used to destabilize this enolate relative to that of ketones, as we have seen before. So this gives us another resonance form which explains, of course, there is a lone pair here on this position. Now this explains the relative less acidity of esters at the alpha position compared with that of ketones. pK here is 25. Again, if we draw the structure of amides, this is amides, NR2. Now this is a very simple amide where there is only like CH3 here. We can draw R if we wish. This is the alpha position. Now if amides are deprotonated, we get the corresponding enolate, which is this one here. So that's the enolate. Again, that's the alpha position. And if you recall also, the pK of amides is 30 in general at the alpha position. So the acidity of that position is reflected in that pKa value. pK is 30. So this suggests, of course, that amides are actually less acidic than esters at that alpha position. So why is that so? Well, to make this enolate, to start with, of course, LDA is also suitable because LDA comes from the corresponding the corresponding amine whose pKa, or the acid, that acid has a pKa of 40, still higher than 30. So LDA is still strong enough as a base to deprotonate amides at the alpha position. Now, the corresponding enolate is formed. Now, just like when oxygen behaves as an electron donating group in esters, nitrogen can also do the same. But the difference is the lower electronegativity of nitrogen compared with that of oxygen. Nitrogen is less electronegative than oxygen, therefore it's a beta electron donor. Donation here, in this case, should be stronger than donation by oxygen. Amino groups in general are stronger electron donating groups than alkoxy groups or hydroxy groups. That's because nitrogen is less electronegative than oxygen, and therefore it's a beta electron donor. So let's write that down. Nitrogen is less electronegative than oxygen. Therefore, this nitrogen is a beta electron donor. The NR2 is a beta or a stronger electron donating group as a result. So donation of electrons by nitrogen is stronger than that by oxygen. So we can do something similar. The lone pair is taken from nitrogen to make a double bond between nitrogen and the carbon-carbon double bond is broken to leave a carbanion on the alpha position. So this gives us this resonance, additional resonance form, and of course a positive charge on nitrogen and this is the alpha carbanion. This alpha carbanion or this enolate is actually less stable, therefore, because of the stronger donation of nitrogen. That's due to the lower electronegativity of nitrogen compared with that of oxygen, and thus nitrogen is a better electron donor. So therefore, this is destabilized relatively, of course, okay, by the stronger electron donating group, which is an R2. So therefore, this enolate or this alpha carbanion is less stable conjugate base. If it's less stable, therefore the original substance, which is the amide, is less acidic relative to the original substance in the upper case, which is esters. Yeah. So amides therefore have lower acidity at the alpha position here compared with that of esters. That's because the relative instability, if you like, of the enolate, of course, relative to that to enolates of esters. That's because of the higher electron donating ability of the amino group, higher than that of alkoxy group, and this is all due to the lower electronegativity of nitrogen. Therefore, the higher electron donating ability of it. This results in stronger donation of electrons, and therefore destabilization of the conjugate base. And as a result of this, and to conclude, amides are less acidic at the alpha position than esters.